In this video, I'm going to talk about a CE configuration, small signal amplifier, CE configuration with the T model. Okay, when do we do the T model or pi model? So if emitter is not grounded, if emitter is not grounded while doing AC analysis, then we'll use the T model. If it is grounded, then we'll use the pi model. I'm sorry again, I'm using my PDF document. I already went through this problem in the class, so I'm going to go over it again for review. So first thing, we have to do the DC analysis. While doing DC analysis, we know that capacitor is going to act like a open circuit. So I'm going to remove all the circuit connected through the capacitor. Now we'll end up with this small circuit. Now we're going to do the DC analysis to find IC. IC is needed to continue solving the AC analysis. So I'm going to do the loop analysis right there. So 100K plus 100K times IB plus 0.7. The voltage drop between B and E, I'm taking that as 0.7. That's 0.7, 8.3 K IE minus 10 equal to 0. So this is the loop equation, and we know beta equal to IC over IB, alpha equal to IC over IE, and alpha equal to beta over beta plus 1. You need to remember these three formulas. So substituting those two, we'll end up with IC equal to approximately 1 milliampere. Okay. From IC, make sure that, from the DC analysis, make sure that this transistor is in active mode. By finding VC and VE, I found that VC minus VE, which is almost 6.61, which is greater than 0.3 volts. So VCE is greater than VCE saturation. So this transistor is in active mode of operation. Now in T model, you have to use the RE instead of RPi. So these are the common formulas, no matter what, whether it is CE configuration, CB configuration, or CC configuration. So transconductance GM equal to IC over VT. VT is given by the manufacturer. It's around 25 millivolt. And beta value is also given by the manufacturer. So from beta, I can find the alpha value. VA, it is going to be either early effect voltage like 100 volts. Sometimes it might be infinite. So those are all already given. So while doing AC analysis, make sure we replace all the DC sources with their internal resistance. And as I mentioned, since emitter is not directly grounded, we're going to use the T model. T model is nothing but, this look like, this is the transistor. That's the base, that is collector, that is emitter. So this transistor look like a T. So that's the reason we call this as T model. Similar to pi model, if you remember, in the pi model, you will have something like this. Okay, so from the bottom, it is look like pi. So that's the reason we call this as pi model. So that's how. Now, when it comes to the R0, the internal resistance of the transistor is always connected between the collector and emitter. Okay, and we will use it only when either emitter or collector or both are grounded. In most of the cases, it is not possible to ground both emitter and collector because you have to use either one of them as an output terminal or input terminal. Okay, but if any one of them are grounded or all of them are grounded, all of them in the sense emitter and collector will use the R0. If not, we'll ignore it. Why is that? If you remember, R0 is approximately 100K, very big resistance. If I include R0 here, my calculations are going to mess up. I need to do lots of calculations, not mess up. I need to do lots of calculations to find accurate value. But at the same time, this is 100 kilo ohms. How much current is going to pass through this? Because I have 5K there. So almost 20 times smaller current than the current passing through the RC. So to avoid the error is going to be minimum. So to avoid all those calculations, we are ignoring R0. So if we ignore the R0, this is how the circuit is going to be. So we need to find the gain. V0, gain is nothing but AV that is V0 over Vn. Okay, so I need to find the relation between V0 and Vn. V0 equal to minus Gm times Vb times RC parallel with RL. This is load resistance, RC and RL. So V0 is right here. These two are in parallel, and Gm times Vb, that is the current passing through this. Based on that, I will end up with a negative. I mean, as mentioned, CE configuration always it's inverted. By the way, the current is going to enter from there, so V0 must be a negative value. Now I need to find VBE. So Vn input terminals are this and the ground. So these are the input terminals. Now the voltage here is Vn, similar to voltage here is also Vn. Okay, but remember, this is not a physical connection, it's just virtual. Okay, whatever the voltage appear here, it's the same voltage will appear there. This is still emitter, this is collector, and that's the base. So the voltage here is also Vn. So to find VBE, I just use the voltage division rule. So the total voltage here is Vn. By using the voltage division rule, Vn times Re over capital Re plus small re. Based on this, I found V0 by Vn, which is AV, equal to minus 2.97 volt per volt. So here my gain is really small. If I give 1 volt, basically it is giving me only 0.297 volt. Okay, instead of amplifying, it's reducing the size. Now open circuit gain is nothing but AV0, which is without RL. So all we need to do is just remove this RL and solve for it. So I'll end up with minus 5.95 volt per volt. Now we're going to find the output resistance. So while finding output resistance, make sure, since there is a dependent source, either you connect it 1 ampere source or 1 volt source to find that value. Okay, now we have VBE. Okay, so I need to find what is VBE. We'll have VBE only if I have a source connected right there. I mean, source connected to the base. In this case, I do not have any source, so my VBE is going to be 0. Since my VBE equal to 0, or if you look at these calculations, I think I proved it by using the calculations. Okay. So my VBE equal to 0, so that means there is no current passing through this circuit, 0 milliampere. So my output resistance is going to be just 5 kilo ohm. Okay, input resistance. I mean, here I solved it, I showed many calculations, but the simple way is to find out the input resistance. Move this resistance towards the base side. So right here, when we move that, all you need to do is just multiply with beta plus 1. Okay, I'm calling it as emitter resistance looking into the base side, RIB. Okay, so when you move the resistance from the emitter side to the base, that value is going to be RIB equal to RE plus RE, small re plus capital RE times beta plus 1. So if you're moving resistance from emitter to the base, it's just multiply beta plus 1. If you're moving the other way, which is base to emitter, then divided by beta plus 1. So based on this, I can find the input resistance. Now you can find the overall gain, GV. I think I didn't find it here. GV equal to always AV times R input over R in plus R signal. This is common, doesn't matter whether pi model, T model, or CE configuration, CB configuration, CC configuration. Okay, thank you. I'll stop this video here. If possible, I'll make a couple of more videos based on the CE, CB, CC configuration. Thank you guys.